engineering domain from IISc Bangalore. Um, Sir's research interests include electrical and electronic instrumentation, data acquisition, aerospace, biomedical, electrical impedance, neuroimaging. So, Sir has worked in academic and research, and also is holding postdoctoral fellowship from various foreign university. Uh, he has 5 book chapters, 37 peer-reviewed journal papers, 39 conference papers in his credit, and Sir has received more than 25 academic awards, achievements, and honors. And he is actively involved in various research activities. So I once again welcome you, Sir, on behalf of Dr. AIT. Thank you.
Hello. Thank you, madam. Thank you very much for the introduction about my profile. So it is my pleasure to be here, to be the part of this FDP. And I'm very much pleased to get the invitation from Dr. Ravi sir. And he is my friend, he is my senior. So we met a long time back in Bangalore in BMS College of Engineering. So it's a nice moment when we met for the first time. He was invited as the expert for evaluation of some thesis, and after that we keep continuing our collaboration, discussion, and all. And now again, I also visited Dr. AIT for giving one talk long time back when I was in ISC. So, and it's my really pleasure to be a part of this FDP. So I will discuss about the impedance-based techniques for biomedical science, though I will discuss a little bit about the other fields also. It's a new field, so I will try my level best to discuss starting from the basic, and after that I will go in detail. So anywhere, if any doubt comes, I will be very happy to explain that. And I will never mind if you ask me in between my talk also. So you are always welcome to discuss for this new topic. So I will share my slides. Hello.
Slide is visible, sir.
Okay. So shall I start?
Yes, sir. Yes.
Okay. Good afternoon, all. Today we will discuss about the electrical impedance-based non-invasive systems, and I will discuss about the technology, instrumentation, and the applications. So electrical impedance-based techniques are generally used for biomedical systems, biomedical applications, which is also found that it is very safe technique compared to the other medical diagnostics. So majorly, I will discuss about the biomedical applications, and also I will discuss about the other applications where the impedance-based techniques are also applicable. So before going to the biomedical field, I think it will be better to discuss very brief about the human physiology and the human anatomy. Though I know that the participants who have attended or who are attending this FDP, they are having the knowledge about anatomy and physiology. So I'll not take much time on that because we need to discuss many more things on the EIT techniques. So first of all, we will introduce that our human body is very complex biochemical system. It's kind of one big laboratory, complex laboratory, and many organs are there, and the organs are associated with their own work as well as the others' work. So all are dependent and sometimes influencing the performance of the other organs. Or all organs are developed with tissues, and tissues are developed with cells. So we can divide our human body or human anatomy or physiology with several systems like muscular system, skeletal system, circulatory system, and all. So as for example, nervous system will generate the signals which could be found as the electrical signal from the scalp, which is known as the EEG. So that type of brain signals are developed to communicate with all other organs, all other body parts, so that all the body parts and all the organs are working together and working as per the protocol to keep our body healthy and alive. Generally, the brain signal which is generated inside the brain tissue travels through the other conducting path, which is developed with neurons. Nerves are say nerves are developed with neurons or the nervous system parts, where we will see several junctions are there, which is called as the synapse. Because the length of the neurons are limited, so definitely there will be several array of neurons, and these all signals are traveled through the neurons from sometimes axon to dendron, sometimes dendron to axon, sometimes receiving signal, sometimes actuating signal. If we say unwillingly step on a sharp stone, we will feel pain, and that is taken as the input to the body, and the sensing part of the skin will give the signal, and that signal will travel to the brain, and brain will decide that it is not good to step up on a sharp object. So definitely it will give some signal to the muscle, and that signal will also travel through the nervous system part called the nerves. And then our actuating muscle will work as per the so instruction coming from the brain, and our leg will automatically bend, and we will be saving our body part. Similarly, for the circulatory system, our hearts are say continuously beating to pump the blood, so that the blood can be sent to the lung for purification, where the carbon dioxide mixed blood will be purified and oxygen will be mixed with the blood, and then again the oxygen mixed blood will come inside the heart, and that heart will again pump it out for sending the purified blood or the oxygenated blood to the all other body parts. So that continuous pumping is always conducted by the electrical signal, and that electrical signal is generated by the natural pacemaker, and that pacemaker is generating electrical signal as a pulse, and that pulse is also that electrical pulse can be also acquired from the surface of the chest using some electrodes, and that is called electrocardiograms. And this is the general anatomical view or animation picture, how that blood is coming to the body. Oxygenated blood is denoted by the red color, and the carbon dioxide mixed blood is denoted by the blue color. So this is a convention which is followed in all the anatomical books or anatomical lectures. So now this was about our human body system. Few of the systems have been explained. So now when we were there, when our science was not so developed and the engineering was not there, so that time also human body was going through several problems, health problems or diseases. So that time also some experts were there who had their experiences, who had their own procedures to identify or to diagnose the diseases. So they are they were known as the doctors and the health experts. So, but that time the procedures were not very scientific. So all the procedures by which they tried to collect the information from the body, those were based on the visual observation, touch sensing, and hearing. So it was not accurate, and sometimes it was creating some life risk also. But gradually we developed our science. We understood several things. We gathered knowledge. We become experienced. We came to know about the human anatomy, physiology. We developed our biological science, and then the healthcare system was developed, which is called as medicine, field of medicine. And then engineering came. That engineering is also uh, the field which will give us several tools to solve the practical problems. And the time when all the fields or few of the fields are combined and they are helping each other, uh, which is known as the multidisciplinary approach or the collaborative, uh, say, approach, which gives us several other discipline or multidisciplinary field like biomedical engineering. So when the biology, medicine, and engineering works together, then the field is known as the biomedical engineering. And that biomedical engineering does two fields, two major work, that is diagnosis and treatment. So first of all, it will detect what type of health problem is there. After that, they will go for the other steps, which is related to the treatment. So now the first requirements are there. Some researchers, scientists, or engineers will be there from the technological field. They will be expert in technology. Then the technology will be transferred to the industry or developmental sectors where the device and instrument will be developed, which will be known as the biomedical instruments. And after that, the doctors, medical practitioners, and the clinicians will use those instruments. That means they will apply those instruments for detecting the diseases or sometimes treating the diseases. So instruments will be like, say, any other tools which are used in our laboratory or practical field, but sometimes instrument may be found as the electrical or mechanical or any other. And the instruments which are used for biomedical purposes, those are known as biomedical instrument. And biomedical instruments are not necessarily will be always of electrical type. That may be optical type, that may be mechanical type, or they may be having different technologies clubbed together, that is electrical or electromechanical, and so on. So modern diagnostic techniques can be obtained as either signal measurement techniques or the imaging techniques. So for the diagnostic purpose, we will apply some tools or techniques to collect the information of the body, which will give us the clue about the health condition. So it may be sometimes invasive, sometimes minimally invasive, sometimes non-invasive, or sometimes non-contact. So for example, if we go for temperature measurement, so we can put one thermometer on the surface of the body or in the natural cavity like mouth or ear, or sometimes we can put some instrument near to the skin, but it will not keep any part of the instrument on the skin, that is, it will not touch anything. So that type of instruments are called non-contact type. The parameters may be either temperature, blood pressure, oxygen saturation, blood count, etc. And imaging means it will be getting the picture of the body or body parts, either directly taken the pictures like with camera. If we go for the surgery room, we will see several pictures are available, or doctors can take several pictures because body or body parts are open. It has gone through the surgery, so we can take the pictures of body interiors with normal camera or any other uh, the imaging devices. But in most of the cases, the medical imaging is conducted with non-invasive mode. That means we will not cut anything. We will apply some signal, and we will collect the response of the body. And comparing the applied signal and the signal received, we will be getting some indirect imaging or indirect procedure by which we will be getting some body tissue picture. So that picture is called the X-ray, what is shown here. Here the X-ray tube will be used for applying the X-ray, and that X-ray will pass through the tissue, that is soft tissue and bone tissue. depending on the tissue density, the X-ray will be attenuated. And with the contrast of the attenuation, we will get the contrast in the picture, which will be exactly similar to the bone structure. So this is very familiar experimentation, which is generally prescribed by the doctors whenever they are suspecting some fracture in the bone or any abnormality in the bone or in the muscle. So that is not only done for the for detecting the bone structure. There are several applications are there, but this is called the planar radiography, and that planar radiography is similar to our light shadowing say phenomena which we followed during our childhood. So we took one torchlight and we put one ball or something else, and we saw the impression of shadow or picture of the object on the wall. So this is a similar technique. Here we can see that the X-ray is traveling in a particular direction, and if there are several tissue layers in the direction of the X-ray path, then those type of images or all images of all the tissue layers will be superimposed. So that is a drawback of the planar X-ray radiography. So we can see that modern biomedical systems will be either acquiring some signals or with either acquiring some tissue information as a lumped parameter. As for example, for blood pressure measurement, say it will be 120 by 80 mmHg. So that blood pressure is giving two values, say 120 or 80. Or ECG voltages will be having, say, several millivolts across the time frame, and also EEG will be also giving some in some microvolts. So those values will be coming from the body surface either as a lumped parameter or as a analogous signal. So that analog signal can be interpreted or correlated with any tissue property or any say body state or either healthy or unhealthy conditions. So comparing those healthy condition data and unhealthy condition data, doctors can get some clue or get some information about the diagnosis. Depending on that, they can detect some disease or they can predict some disease may be there. And whenever they will be confirmed that some abnormality is there, they will prescribe some surgery or procedures, or they will give some medicines to treat the diseases. So here you can see the X-ray planar radiography. X-ray source is there and patient is standing at the opposite side. X-ray receiver or the film will be there. And apart from the planar radiography, when the doctor realized that the several body layers, several tissue layers are superimposed in a single film, so the CT or computer tomography was invented. In computer tomography, you can see that one X-ray source is there, and the source is rotated with a particular projection angle, and we will be collecting all the data across the gantry, and there will be some fan beam shaped or parallel beam shaped or pencil beam shaped. So there will be different kind of imaging techniques. I think so the people who are coming from the medical electronics background, definitely they will be having the concept of different kind of CT. So I will not go in detail. So in case of MRI, there will be the magnetic field which will be applying on the body, and the magnetic momentum of the proton which are there inside our body tissue water, we can get the image of the tissue structure. So similarly for positive emission tomography or SPECT, we can get the gamma rays which are coming from the body tissue after injecting some radioisotopes. And now using the ultrasound, we can also get the images, because ultrasound means the sound which are beyond the capability of human hearing, and that's why it is called ultrasound. We cannot hear that ultrasound, and that ultrasound is a sound wave, and that can travel through a particular medium. In vacuum it cannot move, just like sound cannot move in vacuum. So whenever there will be body tissue, it can travel, and depending on the tissue property, the speed of the sound will be different. And whenever it will get some obstacle that is on tissue, it will be having some property of reflection. Whenever the sound will be reflected back, the receiver will receive it, and it will also be converted to the electrical signal. And that electrical signal will be going to the computer, where there will be signal processing algorithm, and we will get the picture either in static domain or in the say dynamic domain. And there will be fluoroscopy, there will be endoscopy, and a lot more imaging technique or diagnostic techniques will be there for the for the medical field. And all these instruments will be known as the biomedical instruments or medical instruments, and those are all are diagnostic instruments, because these instruments are used to collect some information which helps the doctor to diagnose some diseases, if any. The instrument which is very familiar to us who have visited to the emergency room, I wish that nobody of us will be requiring to visit the emergency room, but still, for our relatives, for our family members or friends, sometimes we need to visit the emergency room, and where we can see that there will be certain instruments looks like this is called vital sign monitors. And vital signs monitors means there will be certain parameters, body parameters, which are very important initially for the quick diagnosis for the doctors. So whenever the doctors will see one patient, they will try to talk to the patient to get some information. If they are not in the position of speaking or talking, means for the patient, so definitely uh, some information are required to be measured, and which is first of all, say, body temperature, blood pressure, heart rate, ECG, SpO2, means oxygen saturation, how much oxygen is there present in the blood. So if oxygenation is not sufficient, then I think that parameter is well known to us, at least after this COVID situation, because this is very important parameter when the COVID-19 virus enters to the body. So respiratory system is affected. Respiratory system is affected means respiratory system will not work properly. As I explained during our anatomical part, first few slides, I told that whenever the blood is pumped by the heart, it first goes to the lung for getting or collecting the oxygen, for mixing the oxygen inside the blood. So that work is done by the alveoli or the say tiny tissue of the lungs. So whenever the lungs are not working properly due to the infection or any other damages, definitely the oxygen mixing will not be as per the requirement. So the blood, people can breathe, but still that blood will be lacking of oxygen. So if the blood doesn't have proper oxygen, metabolism will be hampered. Also brain tissue may be damaged, because brain needs a certain oxygen level. The patient may be faint, or the situation may be life threatening. So those parameters are very important. Whenever the SpO2 will be, say, below 95 or even less, some oxygenation is given from the outside, more oxygen is provided, ventilation is required to be given if the lungs are not properly inhaling. So a lot of complications may be there, and due to that we can read that parameters, whether it is going or in correct direction or not, and immediately the appropriate action is required to be taken by the clinician and doctors. Okay, so this is say little introduction about the human anatomy and biomedical field, how the biomedical engineers are working with doctors, how doctors are using some instruments which are called the biomedical instrument, what type of instruments are there, measuring instruments, signal measuring instrument, imaging instrument, vital sign monitors and all. So those are all basic instruments. Apart from those, there are thousands of instruments which are used for the biomedical diagnosis or the treatment purpose. Now I will go to the field of the electricity, which is used for the diagnosis. That's why impedance based. That impedance is nothing but the electrical impedance. So impedance based diagnostic techniques. So if we go for the history of ECG, we can think about the electricity of the heart. Electricity of the heart is recorded by some instruments and electrodes. These are the sensors. And then these are the instrument which will have essentially some amplifier, filters, and other instruments, signal conditioning devices like digitizer. And then it will be having some memory so that we can store it. There will be some printer attached. May not be printers always. It can be connected to the PC or other external printers so that we can get the signal printed out on the paper. So Eindhoven was the first person who thought about that procedure, and it is his experimental setup. He didn't have any electrodes, sophisticated electrodes like what we have in our hospital right now. So he developed his own electrodes with 3 buckets filled with the saline solution, and that saline solutions are conducting in nature. So he dipped his right and left hands and the left leg on 3 buckets, and he came in contact with 3 sensors or 3 electrodes. So these are the crude electrodes of first time, the electrodes which are used for like electrocardiography. And that electrocardiography machine was very big at the time, but nowadays with the help of the electronic technology or electronics engineering, we have got the several components, tiny components like operational amplifier, transistor and all, and we can nicely design our own electronic circuit and we can manage. So the instrumentation will be having some instrumentation amplifier, and then there will be some isolation amplifier, filters, notch filter, low pass filter, high pass filter and all. And we can get the signals without any noise and with minimal noise, or in a particular amplified manner so that we can record it, we can measure it. These are the instruments. After that, we can go for some other instruments like say either blood cell counting instruments or all blood pressure measurement instruments, sphygmomanometer based instruments are there. So we can put the receiver, sound receiver, so that you can listen the beep or corotcop sound. We can inflate the cuff with the hand pump, and we can stop the blood flow. And whenever it will be very narrow, the blood vessel will be narrowed, it will be blocked. After that, the sound will start coming, and at the pressure, it will come when the air pressure is equal to the blood pressure. And in this way, the air pressure can be visible in the mercury column, so that we can just count the blood pressure. So these are techniques. I am going to skip that. And ultrasound, I have already explained that ultrasound is generated by the electronic machine, which will have a monitor also. That machine will send some electric pulse, and that pulse will be transferred, or it will be changed or converted into the mechanical vibration, and that vibration will be in very high frequency, and it will be generating some sounds which will not be able to be heard by the human ear. And that sound will travel to the tissue, it will be reflected back. Again, the sensors will receive that sound, and then sound will be converted to electric signal, and the electrical signal will go to the computer again. And the applied signal and receiving signal will be compared, and the image will be created by the algorithm. Similarly, in case of the EEG or electroencephalography, we will put the electrodes on the scalp, and our brain will be generating some signals. That electrical signals are in very, say, teeny amplitude in microvolt range, and that will be amplified by the amplifiers here, and it will be visible in the screen. Now, the impedance-based biomedical instruments. How the impedance-based biomedical instruments are helping the doctors in present scenario. First of all, we will discuss about the DC current. DC current means charged particles, either electrons or holes, are conducting in a particular direction. In a same direction it is going or flowing. That's why it is called direct current. In case of alternating current, the charged particles or the, say, electrons or holes, whatever is there, is flowing in a different direction with respect to time. So in how many times it is changing its direction, that will tell us the frequency of the signal, and say how many numbers of electrons or the how much current is flowing, that is amplitude. So there will be amplitude as well as there will be the frequency. So generally, as we use, say, alternators, and it is rotating in a circular direction. So from the circular rotation of the conductors, we can see that the signal is generated in a sinusoidal wave. So alternating signal means standard alternating signal is periodic signal, and that is called sinusoidal signal. Now, whenever the sinusoidal signal is applied to a particular object, it may be a brick, it may be a bamboo stick, it may be some plastic material, it may be a water bottle, anywhere, it will get some conducting path, or it will not get some conducting path. So as per the theoretical perspective, there is no such ideal insulator, so definitely there will be some conduction. And how the material will behave, that material could be represented by the combination of resistance, capacitance, and inductance, and some other parameters, very complex parameters like constant phase element and all. So we will not go in detail because those things will come in more detail in the impedance techniques, impedance based techniques. So I will confine our discussion in the capacitive, resistive, or inductive type of techniques. So now what will happen if any material is taken, that material is not known, means we don't know the electrical property of a material. Suppose we have a block, looks like a brick, but we don't know what is there inside. Then we can send some signal and you can get the response, and you can analyze as per the impedance theory. You can tell the equivalent circuit of that material. Even we are able to get the equivalent electrical circuit of a concrete pillar if we properly inject some current and measure the signal. Now, first of all, if we have a particular resistor, tiny resistor, so there will be the current and voltage which will be in phase. But if there are some resistors along with some capacitor or inductor, or single capacitor is there, or any other material is there which is not purely resistive, there will be phase displacement as it is shown here. So means there will be some reactive component, and reactive component means there will be phase displacement. Here you can see that resistor is there, means there will be in same phase. Inductor means current will be lagging, voltage will be leading, and capacitor means current will be leading and voltage will be lagging. So if there are the combinations, depending on the value of the R, L, and C, we will get certain amount of phase angle. So that will be say below 90 degree, and using the impedance triangle, we can get how much reactance, that is inductive reactance and capacitive reactance, will be developed. And depending on the value of the capacitance or the frequency of the signal, we can tell that whether the circuit will be having some resistive property purely, or there will be some reactive property mixed with the resistive property. If there are some value of the inductance or capacitance in such a way that the XL become XC, then what will happen at a particular frequency, if that is XL equal to XC, then this reactive part will become 0. So it will be purely resistive in nature, and phase angle will be again 0. Otherwise, phase angle will be keep increasing in this direction. So if the inductive reactance dominates, we will tell that inductive circuit. If the capacitance dominates or capacitive reactance dominates, then we will tell that that is a capacitive circuit. So it's a simpler diagram. That circuit diagram may not be simple as always. So there may be several complex combinations. So I took a simple RLC diagram, and depending on the this diagram, that is RLC connected in series across one alternating voltage of the frequency F Hertz, we can get, or you can calculate the capacitive reactance as 1 by omega C and the inductive reactance as omega L. And after that, we will get the phase angle also by this formula. So these are our formula, basic formula, which is studied in basic electrical engineering, the first year of the engineering domain. So there may be parallel circuits also. For parallel circuit also, we can draw the phasor diagram. We can get the phase angles, and the same theory will be applied. And now we will come for the unknown materials. Suppose we have a body tissue, or we have a block of clay. We don't know what is the electrical circuit or what is there, because if we have a block of mud or clay, definitely we don't know what will be the property of the mud. If we see that mud has more sands, definitely its response will be different. If some material is there, less sand. So depending on the composition also, there will be the response different. The response will be different. If there are some certain percentage of water, depending on the component binding with water also, the electrical property will be different. So if we apply some DC current, and if we measure the voltage using the Ohm's law, we will be able to get the resistance of the material along this direction, along the red arrow. But if we apply some AC current, and if we measure the AC voltage developed, then we can get the impedance of that. So now, for the impedance measurement, what we do, we apply some alternating current, because we know that if we apply DC current, then DC has the 0 frequency, so we will be not able to get the proper responses or actual property which is obtained in the AC. So if we apply the AC, we will be able to get the response or collective response or cumulative response of resistance, capacitance, or inductance, or any other circuit parameters are there, we will get as a lumped parameter. So what we will do, we will inject some electrical current, alternating current will develop, we will get the voltage is developed across this. We will measure any 2 points, across any 2 points. So if we have this material, current source and voltage measuring device, it may be a multimeter, but it will be measuring the phase angle as well as the voltage of the material. So if the phase angle is considered as 0, so whatever phase angle will be obtained here, so we will be noting down that. So now after that, after dividing the V by I, so this voltmeter value and the ammeter value, definitely we will be getting the Z, and that will be a function of phase angle theta. And that can be done by two probe method, means current source and the voltage measuring device can be connected to the same electrode. It will having some error because the contact impedance will be also calculated by this voltmeter, so it will be also coming in this circuit, contact impedance. But in case of the 4 probe method, current source path will be different for the voltage measuring path. So here, as the voltmeter ideally collects very less amount of current, so voltage drop across the contact impedance will be very less. So this voltage or voltmeter reading will be almost accurate measurement of the voltage across these blue electrodes. So this is called 4 probe method. So 4 probe method is more accurate compared to the 2 probe technique. Now after that we will come for the tissue measurement. Till that point we understood how to measure the impedance for any material and how to measure the impedance with 2 probe or 4 probe. So now if we have a particular tissue, we don't know what type of tissue is there. So what we'll do, we will inject some current, and that current will have certain amount of frequency because it is alternating current, so frequency will be there, and that frequency will be changed gradually, and at all frequency we will be measuring the voltage. And that technique is called electrical impedance spectroscopy. So electrical impedance is understood by this diagram. Now here S is there. So electrical impedance spectroscopy. S means spectroscopy. Spectroscopy means, scopy means getting some particular image or response. Scope is used for measuring some parameters, oscilloscope. So that type of spectroscopy means there will be a word spectra, and that spectra is nothing but the spectra of frequency. So there will be a certain amount of starting frequency and ending frequency. So we will start at say 10 Hertz and we will stop at 10 kilohertz. Between 10 Hertz to 10 kilohertz, we will be changing some frequencies and we will be measuring the impedance. And if we plot the impedance real part and impedance imaginary part, then we will be getting some Nyquist plot, and that Nyquist plot is very vital for impedance analysis, because if we analyze this type of curves, which is obtained by say, a circle or semicircle, that will give us the equivalent circuit of the material. So if one semicircle is there, that will be parallel combination of resistor and capacitor. So if there are several circles, there will be parallel combination of other. So this block will be there again. And if there is any difference between that, means starting from the origin, if it is the circle doesn't start from origin, that means there will be a series resistance. So there are several theories about the impedance based techniques. So after getting the impedance from the impedance spectroscopy data, we'll be able to draw the Nyquist plot. And whenever Nyquist plot will be drawn, analyzing the Nyquist plot, we can get the equivalent circuit of the material. And that circuit material will have certain capacitance values and resistance values, series capacitance, parallel series resistance, parallel resistance, and all. So those parameters will be related to the tissue properties. And if we see that for normal data, the resistance is changed, then you can tell the tissue is not in the normal condition. So if we have a data set for the normal tissue, definitely we will be able to compare with that. And this technique is very say safe, and that technique is portable. The technique is dry kind of technique. No laboratory experiment is to be done with chemicals. So simple, we will have some instruments which will inject some current, small amount of current, 1 milliampere, and you can change the frequency and you can get the data from the tissue and you can get the tissue properties. So we have already explained that slide. So Luigi Galvani, we are thankful to Luigi Galvani who first indicated that interaction between electricity and the muscle tissue. So that was the first day when people realized there is the interaction, there will be some relation between electricity and the muscle or the body analysis. So now how the impedance will be coming from the body. So where the resistance are there and where the capacitance or inductance are there in our body tissue. Is there any real inductance or capacitance which are obtained in our laboratory? No, definitely not. But the material is there in our tissue, in our body. Water is there, muscle tissue is there, fat is there, bone is there. So all will have its own properties, and that property sometimes matches with some capacitance or some resistance. So that's we are going to explain here. So the basic unit of our body is cell. For the plant, it is plant cell, and for the animal, it is animal cell. Now, whenever we will see that any muscle, the muscles are developed with say tissues, and tissues are developed with cells. They are arranged in a three-dimensional cells in different directions. Even for the plant also, if we cut the say plant tissue, then we will see several tissues are arranged in a different manner so that we can get the three-dimensional structure of the body tissue. Now if we take an animal cell, say this is one animal cell, and if we cut that cell, then we will see the protein lipid protein bilayer structure for the cell membrane. So red color is showing the protein and yellow color is showing the lipid. So there are protein layers outside and the lipid layer is inside, and that lipid layer means oily medium, so less conducting medium, and protein means water loving medium, so it is highly conducting. So two highly conducting mediums are sandwiching the non-conducting medium, and which is giving us the concept of the capacitance. And so we are getting some cell capacitance. So whenever we will take one cell, isolated cell, we will get some cell capacitance from its membrane. So if we have one cell isolated or surrounded by the extracellular fluid by this pink color of domain, and if we see that green colors are the protein and the pink color is the deep pink is the say our lipid, then we can get two conducting paths at at such a particular frequency. So current may be traveling to the cell or current may be traveling to the extracellular fluid. For lower frequency, capacitance works like say open circuit. So definitely the DC current cannot pass through the capacitance or cells. So for low frequency means if the frequency is nearer to the say 0 or say below certain kilohertz, we will see that the current will try to flow through the extracellular fluid, because extracellular fluids are developed with salt solution and very conducting medium, and that property is the resistive medium. So the impedance of that path will be less compared to the impedance of cell. But if we increase the frequency at higher frequency, so capacitance will provide a very less impedance or less reactance. So current will be also trying to flow through that part. So current will be divided and it will be flowing through the cell as well as cell membrane. And using this diagram, we can get the cell equivalent circuit of this type. So there will be cell membrane and there will be intercellular fluid resistance and extracellular fluid resistance, and they will be connected in parallel. And as the current is flowing in this series, so definitely current passes through that, same current is flowing through that, and same current passes through the series circuit only. So that's why the cell capacitance and the intracellular fluid resistance, that is RICF, are connected in series. So this is the model. Many other models are there, and if we study the multi-cell responses, so if we have one tissue which has two-dimensional picture of multi-cells, and if we see that current is about to flow through two electrodes, so low frequency means there will be 1 by omega c, and that will be the Z. And if the current is seeing that impedance is very high, because this is nothing but omega is very less, so this will be very high, so current will be, so total denominator will be very high, so current will be 0. So current will be passing through the extracellular fluid only. But if we increase the frequency, current will be passing through the extracellular fluid as well as it will be passing through the cells. So now if we measure the impedance at two frequencies, low frequency and high frequency, so definitely we will be able to get the impedance of the cells and impedance of the cell extracellular fluid separately. So depending on that property, we can develop the bioelectrical impedance analysis, and we can get the tissue composition, like say how much fat is there, how much muscle is there, total body mass, and all these parameters can be detected, and which is very, very means important for detecting several diseases, even like the cancers. So if any impedance analyzing device is there, just for sending the current and low frequency to high frequency current and measuring the impedance, either at the two frequencies or many frequencies, we can be able to get the body information which is related to the disease. And if we do the simulations part in the either NCS or console, we can also see the same thing. Whenever the cell membrane will be there, current will be trying to passing through at low frequency, passing through the cell membrane, through the extracellular fluid, and very less amount of current will be passing through the cell membrane or cell. But whenever the frequency will be increased, almost it will be considered as the homogeneous medium, and current paths will be parallel to each other. So that can be also studied by these pictures. Here you can see the cell pores are there and cell membrane pores are there. So current sometimes will be passing through the cell membranes at the high frequency and not through the cell membrane at the low frequency. So this is the bioelectrical impedance analysis techniques. And here we can see that utilizing the bioelectrical impedance property, we can measure the impedance of a particular body parts. Here you can see that BIA or bioelectrical impedance analyzer is there. 4 electrodes are there, 2 reds and 2 blue. 2 reds will be sending the current. So this red path will be taken. As this part is not connected to the circuit, so current will not pass through that. And after that, voltage will be measured. So voltage also will be measured across this path only. And this part means this is symmetrical. So if we get the impedance of this path, so the impedance of this path will be also obtained or calculated. So using several formula, we can calculate the total body water, total body mass, BCM or TBW. And those things are very, very important for detecting several type of diseases, especially for the malnutrition and all. So now utilizing the admittivity, this is the recent trend. So utilizing the complex admittivity, which contains the conductivity as well as the permittivity, we can get the tissue impedance, tissue property with more information, because we are getting the permittivity also. So depending on the tissue property, we can detect some tissue healing. If a big wound is there and if it's getting healed for a long time, we can continue the test with the impedance analysis, and we can tell that what is the status of the wound healing. Even for the skin cancer also, it is possible to be detected, because whenever there will be skin problem, if the skin tissues are changed, so definitely its impedance will be changed. So depending on that, even for the food analysis also, impedance based techniques are used to detect the freshness of the food, especially for storage foods. If there are some say deterioration in the food tissue, or which is not good to consume, so definitely that can be also detected by the so many works are detected for the many works are conducted for detecting the food contamination. So as a summary, we can use the electrical impedance technique for bioelectrical impedance analysis, which is used for body composition analysis. We can use the technique for measurement of the blood flow. So if we use 4 electrodes or even 2 electrodes also, we can get the blood flow, that is called plethysmography. So impedance plethysmography, that instrument is developed by BARC India. So many people are also working in this field. So portable instruments that is used for detecting the deep vein thrombosis, which is sometimes found for long traveling through the air. And for the pregnant women also, this deep vein thrombosis is also there due to the hormonal problem, and also it is always suggested for the pregnant women so that they can walk in the flight with the consent of the say cruise member, so that the blood circulation is kept normal. Otherwise, they are very prone to the development of the deep vein thrombosis, especially for the pregnant women. So impedance cardiography is also for measurement technique, where we can measure the impedance of the transthoracic region, putting the electrodes on the neck and the below sternum area, and we can measure the blood volume, and which will give us for analysis of stroke volume and as well as the cardiac volume. So this type of parameters are very, very important for detecting the healthiness of the heart, or hemodynamic analysis is possible to be conducted with the help of these parameters. What is done? We will put the electrodes and we will give the current, and we will measure the impedance variation, and that impedance variation or the delta Z is compared with the ECG, because ECG is the electrical signal variation in the heart, and due to the electrical signal variation, heart pumps, and due to the pumping, the blood going out and coming in, and that variation will be there, and that variation is obtained by the impedance variation, because blood is very much conducting, and that blood is not there means it's a less conductive medium. Whenever blood is more, that means high conducting medium. So that impedance variation is there due to the blood flow, and that is related to the ECG. And after analyzing the signals, we can apply several formula, as for example Schremek formula. So Schremek formula is also given here. So Z0 is uh, the parameters which is obtained from this signal analysis, and after that we will be getting the time variation, that is dt, and then uh, left ventricular ejection time. We can use that formula and we can calculate the stroke volume. Stroke volume means amount of the blood exerted by the heart for single stroke. And after that we will be getting the impedance spectroscopy, and that impedance spectroscopy is nothing but the studying the impedance with a particular frequency spectrum, and that impedance spectroscopy can be applied for this plethysmography also, means we can measure the impedance either at a particular frequency or several frequencies also. So these are the all other formulas like QB-Sec formula, Schremek formula, Nyberg formula. So utilizing this, there will be several differences, but that differences will not be very much, but there are the differences in the formula. So whenever we will have the Z0, we will be able to get the hemodynamic parameters. So impedance spectroscopy means we will having some electronic instruments which will have current source and which will be having some measurement device, that is voltage measurement device. Sometimes voltage signal is also applied and current can be also measured. Now current will be injected at a particular frequency, and after that frequency will be changed from F1 to F2, and then all the data will be measured, that is Z1 to Zn, and all the corresponding phase angle will be measured, theta 1 to theta n. And if we get the real part and imaginary part, we can plot that in a, this will be x-axis and this will be y-axis, and we will get that type of parameters for the profile, and that profile is called Nyquist plot. And analyzing that curve, we will be able to get the equivalent circuit of that. So we can study the vegetable freshness with the electrical impedance spectroscopy. If we study that with the different days, if we go for vegetables, we can see that there will be, say, a distinguished profile difference. So we can differentiate the first day impedance with the, say, 1 week later, the impedance will be much higher, and that is due to the dryness or the loss of the freshness. Means if we keep the vegetables, it will be due to the normal drying, it will be getting old, so it will be losing some moisture, and automatically its tissue will be damaged day by day, and that's why we don't like the old cucumber or old vegetables. Even for the for distinguishing the vegetables also, there will be different impedance parameters. We can see that cucumber will have a lot of water, that's why its impedance is less, but in water is having less water, so definitely it will be having high impedance. So depending on the impedance techniques, impedance measurement techniques, 2 probe and 4 probe data also will give some different data, but we will prefer the 4 probe measurement techniques. So here we can see that, say, potato, apple, carrot and cucumber will have different impedance parameter or the reactive part for its own values. And if we go for the boiled or unboiled vegetables or some tissues also, we will see that there is a big difference for the boiled. Whenever there will be some boiling phenomena, means the tissue will be damaged or the cell membranes will be damaged, automatically it will lose a lot of reactants and its impedance will be drastically changed. So if you want to measure the conductivity, we have to keep we have to keep our measurement techniques with uh, some isolated samples, and that samples will be having a distinguished say shape, known geometry will be there, then only we'll be able to calculate the conductivity. So what we did, we cut the samples with a particular rectangular block, and we put in the stainless steel electrodes, and we can get the impedance data by impedance analyzer, and after that we calculated as per the geometry. Even for the boiled green banana can be giving some very less impedance. So these are the say impedance data for cucumber for day 1 to day 16. You can see that at the day 1 it was less impedance. After that impedance is increasing, means water is reducing. Here this is the water and the days. So weight is measured, and we can see that how the water is affecting its age and as well as its weight. And this is the plot for the green banana, fresh banana, and boiled banana cortex. And this is the say green banana and green banana boiled. So boiled is the blue one, and red one is the green one. So whenever it is boiling is there. So from this technique, we can also judge that for the burning patient also impedance analysis will give us the data to detect the degree of burnt, how much tissue is burnt or how much tissue is not burnt, how much tissue is still healthy. So what type of treatment is required. So that is a good direction. And also for we have also developed the LabVIEW based data analytics technique. Whenever the data will be available, that will not be in the circular path. So carb feeding is required, and whenever the carb feeding is done, we'll be able to get the parameter values as we have found. So we started with 2K register and 1 micro farad capacitors in breadboard. We got the data, and that data is plotted here and fitted, and we got the capacitor values. So original values was that, calculated value is found like this, and register. So this capacitor values is more, error is because capacitor was 5% tolerance. So it was not 1 microfarad, but we took that it is 0.1 microfarad. So that's why that much difference. But if it is measured by impedance analyzer, so definitely it will be having some less error. This is for the cucumber. We have also calculated the parameters. So I'm going. Okay, Professor Ravis, how much time I have? Hello, madam. Okay, so for the food quality detection, we can also apply the same thing for the fruits, vegetables, meat quality, fish quality, milk quality, juice quality, tea leaves quality, coffee quality. Am I connected? Hello, anybody can hear me?
Yes, sir.
Okay. Yes, sir. Okay. Thank you. Okay, so till now many studies have been conducted for the freshness of fruits, freshness of tree leaves, freshness of coffee quality. So materials either may be biological or non-biological, some dried materials like coffee seeds and all. So we can use that technique, EIS. EIS is used for disease detection, as I told, body composition analysis, body tissue aging, tissue swelling, edema, urinary bladder infection, cancer detection, tumor detection, infection, wound healing. A lot of techniques, a lot of diseases are studied with the technique. So now wireless EIS techniques are also possible. So we can put the electrical current injector, and that will be generating some data, and that can be sent through wireless technology. And any clinical center or clinics or hospital, there may be some other biomedical engineers who will receive the data, and they will analyze the data, and they can get the information about the tissue. That is also always there. So now I will come to the imaging part. So whenever we will get some lumped parameter, so it will not display the anatomy of the body. But if we want to see the anatomical representation of any body or body structure or cross section, we have to go through the imaging, just like planar radiography or tomography. Tomography is the best. Röntgen invented the planar radiography. Planar radiography has a tissue superimposing problem. And especially for the brain, if we go for the planar radiography, we will be getting the image of the skull. So skull is very thick and we will not be getting the image of the inside brain. So that's why planar radiography fails, and we have to go for the tomographic imaging. Tomographic imaging means it will give the image of cross section. Any cross section can be taken. Say transverse plane is the most popular plane where the tomography is done, though sometimes in the different plane also is possible to be conducted. So we will get the image of the cross section looking like this, but we will not cut anything. So it is non-invasive. It will not destroy any body parts. So that's non-destructive also. So Alan Cormack and Godfrey Hounsfield got Nobel Prize for that invention. So they, in that field, in that system or instrument, there is a rotating X-ray beam, and it will be rotating and projecting the X-ray beam through the object under test, which will be kept inside the gantry. And gantry will have a circular array of the detectors. And whenever the detectors will receive the X-rays, that X-ray data will be compared with the applied X-ray, and then the two type of values will be compared, and that will be used for the construction of the images. That is called image reconstruction. This is a picture of the components. So advantage and disadvantage. Advantage means it will give high resolution images. First of all, many other advantages are there. Main disadvantage is that it is using X-ray, so continuous CT is not possible. Even there is a certain number of CT which can be conducted per year. So any patient cannot go through the clinic and they cannot go through the CT procedure say every week. It is not possible. It is very, very dangerous. So that type of precautions must be maintained. For MRI, there are several advantages. Resolution is always there, very good resolution. And disadvantage means there will be strong magnetic field. So if any patient has any body implants, metal implants, pacemakers, they are not allowed to go inside the machine. And gamma camera is nothing but one kind of nuclear medicine where the radioisotope or some small life radioactive element which is produced as a medicine is injected, and when this medicine will interact with the body tissue, it will emit some gamma rays, and that will be detected by gamma camera or gamma ray detectors. And whenever that gamma camera is rotated in a different direction and take the projections at 360-degree angle, just like the tomography, it is called single photon emission computed tomography or SPECT. Whenever two gamma cameras are obtained at a 180-degree direction, then this technique is called positron emission tomography. So there are several other techniques, angiogram, or that is used for the cardiac blockage detection, but this is different from the angiography. This angiography is used for the for detecting small artery or veins after injecting some materials, radioisotope materials, which will be fluorescent materials and which will give us the picture, better picture. And for the fluoroscopy, it is also one kind of live imaging technique with the help of X-rays, and that is also conducted after injecting some contrast medium. And mammography is one kind of planar X-ray radiogram, and that planar X-ray radiography is conducted especially for detecting the breast cancers. Ultrasonography we have already discussed, so I am going. Now I will come to the electrical impedance tomography. Now we understood the electrical impedance, how it is helpful for detecting the diseases, and what kind of techniques are available, major kind of, like impedance analysis technique, impedance spectroscopy, impedance plethysmography, impedance cardiography. But all those techniques were the signal measurement techniques, means it was only giving us the lumped parameter or the parameters over the time. So we are getting only values. We didn't get any picture. But here we are going to discuss about electrical impedance tomography, where we will get the picture of the body. Means just similar to the X-ray tomography where X-ray was used, but here we will use the electrical current. So spatial distribution of the electrical conductivity or resistivity will be within a closed domain is reconstructed from the surface potential. So what we'll do, we did the impedance techniques, we injected current, measured the voltage. What we'll do, we will shift the position of the electrodes and we will get the other data. So this is also non-destructive testing and non-invasive technique. So let us consider a circular domain is there surrounded by several electrodes, and that several electrodes will be surrounding the domain, and the different colors are given to indicate that blue electrodes are for voltage measurement electrodes and red electrodes for current injecting electrodes. So current source will be there and current will be injected. Depending on the medium profile, there will be current paths and there will be equipotential lines. So now if we have one voltmeter or any voltage measuring device, we can get the voltage data across two electrodes. So we will measure all the voltage data pairs and we will send the data to the PC. So how the image will be produced, how the concept of or the information of the internal domain is coming from the outside domain. If the domain is homogeneous, we will get the symmetrical current paths. But if we have some object, then current paths will be distorted. If the object is highly resistive, then current paths will try to avoid that object and current paths will be distorted. Depending on the distortion of the current path, voltage distribution will be different. And as the boundary is the last part of the domain, so definitely it will also have the influence of that object. Means it will be also having different voltage data profile. And that will be giving us the internal impedance response. So X-ray tomography is nothing but the tomography which uses the X-ray. And computed tomography with electricity or current is called current tomography or electrical impedance tomography. It was invented by John G. Webster and R.P. Henderson in 1978. And after that, David Barber and Brian Brown tried to use the technique for the biomedical application or medical application, started with their arm imaging. So it was non-invasive, radiation-free, low-cost, portable, just like one laptop and 16 electrodes are there. Small electronics or electronic circuit is required, which can be confined to a portable hard disk. So that type of volume of the instrument is required. It is possible to be conducted with bedside patients which are very ill or critically ill patients which are there in ICU. But for computed tomography like X-ray or MRI, all the patients must visit to the imaging room. That imaging instrument cannot be brought to the patient's bed. Suitable for ambulatory monitoring, means long-term monitorings, and no patient preparation is required. So after that, this technique is not only for medical diagnosis. It was started with the medical diagnosis, but after that it finds its application in process tomography or industrial application. Industrial application means if there are some chemicals inside the vessel, and if you want to see the reaction, then also we can put the electrodes and you can see the chemical resistance or impedance with different colors. So you can see the mixing. After that, biology means cell culture imaging is also possible with the help of microtechnology or microelectronics technology. You can put some microelectrodes and you can see the cell culture, how the cells are developed or cells are making the colonies or cells are dividing. So all these things can be possible to be studied in biotechnology and microbiology. Defense field, if we put the electrodes on the ground and if we measure the soil impedance, we can see that there are some other objects, and that technology can be helpful for detecting the mines, because the impedance of the mines is different from the soil property. And even for the civil engineering, the concrete structure, concrete crack or concrete void can be also detected with the help of electrical impedance tomography. For the geological engineers, it is very helpful tool for detecting the water below the ground or any minerals inside. Current detection technique, current applied technique or voltage applied technique. So when the voltage is applied and when the current is applied and voltage is measured, it is applied current technique. When the voltage is applied and current is measured, that is called applied current technique. But in any case, we have to measure the data of the 360-degree rotation, means total boundary will be covered, but changing with the position. So this is the first projection, electrode 1 and 2. After that, the voltage measurement will start from 3 and 4 and it will stop at the 15 and 16. So one voltage data matrix will be obtained. After that, current injection will be changed 2 to 3. And after that, 4 to 5 will be starting point, and then another 13 data will be obtained. So in this way, we will keep measuring all the projections. We will change the current electrodes and we will get 16 projections and we will get 16 into 13, that is 208 data. Sometimes some research groups are measuring all the data. So 16 is 16 minutes, 256 data are also possible to be detected for 16 electrode system. If we increase the number of electrodes, data matrix will be also large and computation time will be more. Now, what is the logic of the reconstruction? First of all, we have to have some real domain, means the patient will be there with electrodes. According to the patient's geometry, there will be a computer domain, there will be a calculated domain, means there will be a geometry created in a software, as for example MATLAB. And after that there will be some nodes will be detected with the help of finite element method. So the entire domain will be discretized, and then the nodes of the electrode position will be detected, and one current will be simulated similar to the current whatever is injected here. And then the algorithm will start with the assumption of sigma 0. That means the computer will assume the domain conductivity is homogeneous. And for that, one kind of voltage data will be obtained, that is called calculated data, VC. And real data will be VM. As the body is not homogeneous, the real data will differ from the VC. So there will be one data mismatch, that is del V. And that del V will be used to update the conductivity from sigma 0 to sigma 1. And that updated sigma 1 will be applied, and again the voltage boundary matrix will be obtained, which will be again compared to the voltage measurement data. And that loop will run until unless the sigma k or sigma k plus 1 is obtained in such a way that this error or the voltage mismatch is minimized. So voltage measurement data is compared with VC. Del V is given to the computer so that it can update the conductivity, and that conductivity, updated conductivity, will be obtained as a picture. So this is a simulated result. Different object can be made in computer giving some different properties, and if we get the data, simulated data, we can reconstruct in this way. So this structure is visualized in this way. So smaller domain, different structure, different geometrical structure also can be possible to be detected. And this is the instruments. It will have some current injector, signal conditioner, data acquisition system. So it is EIT electronics. Then PC based image reconstruction algorithm. PC based image reconstruction algorithm will be the computer program, and the signal conditioners means instrumentation amplifier, 50 Hz not filter, bench pass filter, and all. Phantom means there will be some models which can be developed before applying that instrument to the human body. We must test with the models, and that is called the EIT phantom. So I will explain that. So electronics will have, as it is shown, that current injector can be developed by the voltage control oscillator, and then voltage control current source, means it will be voltage to current converter actually. So VCO will be there, VCCS will be there. Then switching the electrodes, because we need to measure the voltage of different electrodes, where we have seen that we have to connect the voltmeter with different electrode pairs, but manually connection is not possible for large number of data. So that's why multiplexers or any other switching device, electronic switching device, can be used. So if the multiplexer is used, then all the electrodes will be switched by multiplexers, and then the data will be going to the instrumentation amplifier, then filter blocks and voltage measurement, then it will go to the PC for processing. And all the blocks are electronic device, so there will be some ICs which can be only operated when they are fed by their DC bias voltage. So regulated power supply or RPS is required. So all the instruments will be connected so that it can get the powers. Marks will be also connected, and then voltage control oscillator will give the voltage. Voltage will be converted to the current by VCCS. Current will pass to the marks. Any two electrodes, suppose 1 and 2 is there, will be selected first, and then voltage measurement will start, and that voltage data will come to the instrument amplifier from Fiedler blocks and the voltage measurement device. So instrumentation can be developed with the help of analog and digital electronic circuit, which looks like a simpler board. It looks like, say, computer motherboard also. Can be developed either in entirely breadboard also, but it will be noisy For connection problem, we can make it on the PCB, either general purpose PCB or specifically printed PCB. So all these instrumentation procedures are very basics, and we can get that type of board after the finishing of the instrumentation. So what we have to do: current source, electron switching module, voltmeter, and PCB based reconstruction. Electron switching module also possible to be made manual for lesser number of electrodes, but if you go for higher electrodes, manual will be very much time consuming. So regulated power supply using one transformers, then the rectifier ICs, where you can see that 4 rectifier ICs are there, and 4 level voltages are there: 5 volts, 9 volts, 12 volts, and 15 volts. So depending on the different ICs, we can get different voltage levels. And for all blocks, there are 2 ICs, that is 78XX series and 79XX series. Dual supply can be obtained. After that, this is the complete PCB of the multi-frequency VCO. This is MAX 038 IC, which will generate the sinusoidal signal. After that, modified Howland VCCS developed with 8829, and that voltage signal will fade here, and that will be converting the voltage signal to the current signal. And that current signal will be sent to the multiplexer board, and multiplexer board will give the signal to the phantom. Phantom will develop the voltage. That voltage will come to the instrumentation amplifier, notch filter, and band pass filter, and after that it will go to the computer. So this is the initial stage of the instrument what I developed during my PhD. So this is the manual multiplexer board. This is the phantom, and this is the voltmeter I used, and this is the notch filter and band pass filter, and this is the power supply. This is also another power supply. So I think all the boards are explained. Now we'll go to the second phase. Here we have replaced the manual multiplexer by the AD in the CD 4067 BEIC Texas Instrument. That multiplexer 1:16. So for 16 electrode switching with 4 probe method, we need 4 multiplexers. And if we go for the animation, we can see that this movie tells us that these 2 are the current electrodes. So these 2 will be fixed, and other measurement will be gone. So it will be scanning entire geometry for 360-degree angle. So current electrodes are changing, and the voltage electrodes are moving in a loop for a particular projection. So when it is made PC based, so we use the National Instrument DAC card in a USB 6251 DAC card, and it will be connected to the computer. Other things are there, and this is the final battery based system. This is the phantom with high resistive material simulating some bone structure, and this is the saline solution simulating the muscle structure. We can see that the high resistive material and low resistive background. So what is done in a particular phantom? Domain is taken, diameter is measured, and it is given to the computer. Computer makes one geometry, and that geometry is discretized by finite element method. Electrodes are positioned, and then it is solved by the reconstruction algorithm, and we get the picture of this domain. So this is the phantom measurement procedures using some glass beaker. Sometimes plastic beaker is also possible to use. Gems clip, paper gems clip are also possible to be used as the electrodes, but these are not stainless steel based clips, so that's why it was prone to corrosion. And after 5-10 experiments, there will be some corrosions, and we found that there will be the impedance changes in the electrode points. So those are not suitable for long time use. Stainless steel electrodes separated by the silicon rubber band is also very suitable for practical imaging. And after that, we tested several phantoms, say non-biological phantoms with saline and the plastic and wooden cylinders, then hybrid phantom, non-biological material and biological material, entire biological medium, chicken fat, chicken tissue, chicken fat, chicken tissue, and chicken bone, chicken tissue. This is the say graphical user interface developed in LabVIEW so that we can control the entire instrumentation. Several electrodes have been studied. Sometimes carbon electrodes are used. Sometimes say flexible electrodes are used. Active electrodes are also used. Active electrode means the electrodes will be attached to the instrumentation which will inject the current. So any number of electrodes can be used, though general procedure is to 16, 32, 64, depending on the multiplexers designs. Some microelectrodes are also being studied by UCL College London. They are working on the rat brain imaging with the help of EIT. This is the active electrodes. These electrodes are having some electronics with its each position, a little bit costly. Compound electrodes are also possible. And this is the commercial instrument for EIT developed by the Drager Medical Germany, and this is the belt and is used for the pulmonary studies. If we use the belts for different stacks or in Z direction, then you can go for the say 3D imaging also. Application, say transthoracic imaging. We can see the cross section of the lungs and heart. This is the picture from the Rensselaer Polytechnic Institute. Here you can see the biomedical imaging is conducted in the transthoracic region. Neonatal lung imaging is also conducted with the help of EIT. Breast imaging is possible. This is the instrument for breast EIT developed by Dartmouth College, USA. And brain studies is also possible for human body with the help of EIT technology. And as we have discussed, that cell culture imaging is also possible with the help of microelectrodes. These are the instruments commercially available. This is a breast EIT developed by RAS Russia. This is Drager Medical Pulmovista 500 from Germany. And this is the instrument developed by the collaboration of the University Sheffield and one hospital there in UK. So I will play this movie. If it runs, you will see that how the Pulmovista 500 instrument works. This Pulmovista 500, where the dynamic imaging is possible. The respiration is visualized. Same, the chest region is drawn in the computer. So electrode belt is put on the lung. So present research trend, wearable EIT. Some groups are working on the wearable EIT for getting the dynamic image of the wrist. And breast EIT is also possible, published by this journal, IEEE Journal of Solid State Circuits. And chest imaging with a flexible belt by KAIST, South Korea. And if we increase the number of belts in a Z direction, we can get the 3D imaging also. And EIT is also possible to be utilized for material science, as I have already discussed. So during my postdoctoral research, I have developed the instruments for studying the aerospace material, that CFRP material. CFRP is carbon fiber reinforced polymers, which is used for aeroplane manufacturing. And there I have worked on the 32 electrode EIT. And as the 16:1 multiplexers are possible to be cascaded with another 16, so that we can get 1:32 or 32:1 Mux device. So here you can see that 2 multiplexers are used for Mux V2 and that 2 for Mux V1. These 2 for Mux I2 and this is for Mux I1. That means this Mux is switching the electrode, current electrode 1. This marks is switching current electrode 2. This marks is switching voltage electrode 1, and this marks is switching voltage electrode 2. NI device is also used. NI USB 6360. This is the graphical user interface, entire instrument, and this is the carbon fiber sample. Even for industrial imaging, the opaque pipeline can conduct several materials which can be visualized with the help of EIT also. Using the 3D printing, a lot of phantom development problems are solved, and using the 3D printing technique, we can get precisely designed 4-probe technique. Here you can see that 4 probes are there, and there are 4 cell for 4 well. We can put the solute or the biological samples, blood or something else, and you can conduct the impedance spectroscopy. And if we conduct the same thing for electrical impedance tomography, it will be also creating the same thing or with more accuracy. So here the skull is developed with 3D printing device, and with the help of the 3D printing technology, accurate development of skull is possible. And using that accurate skull, phantom experiment on the brain or on the chest is also possible. So 3D printing is helping the EIT technologists so that we can get more accurate data from the phantom. So as a conclusion, physiological monitoring is required to study the human health and disease. So sometimes wireless physiological monitoring enables us to remove the connecting the wires or flexible measurement instruments. So sometimes IoT technology are also possible to applied for the EIT, and using that technology to communicate with the patients which are staying in the remote place. So recent trends in the wireless technology and IoT based EIT techniques, impedance based techniques like BIA, IPG, IC, and EIS and EIT can be used for physiological monitoring. Wearable EIS or EIT systems have a lot of potential in the medical diagnosis in future. A number of research opportunities are there. Impedance based techniques for materials analysis is a domain, big domain, and 3D printing technology is also a new technology which is associated with the EIT. So I thank my institute NIT Durgapur for my present position, for giving me opportunity to continue my research here and also teaching. I would like to thank Professor D.K. Ravis. I thank the EIT, that is Dr. Ambedkar Institute of Technology, Bangalore, Department of Medical Electronics of Dr. EIT, all the faculty members, FDP, and all the participants who have spent their valuable time for listening my talk. And above all, I thank my all collaborators with whom I am presently working, and I worked for getting some experience and knowledge. Thank you very much.
Yeah, thank you, Professor Tushar Vera. Now the forum is open for the participants, the researchers, serious researchers who can get benefit from the resource person. Any queries are there, will be welcome.
Sir, I want to ask. This is a sir a very nice presentation. I learned a lot, mainly the electrical impedance tomography. Sir, I want to ask you one thing that when the this sensor locations are rotating around a circle, so in that case, the Nyquist plot where is a small peak and a big circular peak are there. So they are how the shape of the time shift of the this plot this signal shape is getting changed. So sir, it is almost middle of your slides. So you show that there is a capacitance and resistance uh, with some another impedance. Uh, so
I understood. Actually, those two techniques are different. Fine.
okay.
So here in this slide, I will again play. Here we have 4 electrodes. Fine.
Yes,
And
sir.
this is electrical impedance spectroscopy. And
Mm-hmm.
we are not changing any electrode or rotating any electrode here.
Yes, sir. Sir,
Okay.
before that slide, I think that before this slide, there is a small peak and there is a
Okay.
larger peak
Okay.
at
Okay. 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 Okay.
one in single dimension. You see this is Nyquist plot of a resistance and a yes, sir, this one.
This one.
Yes, sir, this one. So,
Okay.
sir, here actually the EI is actually changing through the circuit. So, the in that case, the shape of this red diagram of the right hand side, the small peak and the larger peak, how they are getting changed according to the rotation of the voltage sensor.
Okay. So the first of all, this peak is a particular frequency domain. You can understand that. So this is
Yes,
the
sir.
frequency scale. Fine.
Yes, sir.
So if the starting frequency is this, say it's from 10 kilohertz to
$20 kilohertz.
say this is 50 kilohertz, fine.
Okay.
We will get one peak. When the 50 kilohertz will be crossed in higher frequency range, automatically there will be some other response. Means if the capacitance is there or other blocks are there connected here, similar block may be in parallel because there are two circular arc means there will be two parallel blocks connected in series. Fine.
Yes, sir.
And the value of the capacitance will tell us how much reactance will be there.
Yes,
So
sir.
this capacitance and that capacitance here in the second block will be different. And that's why they are responding in different two frequencies, because capacitive reactance, that is the peak value,
Yes, sir.
is is controlled by the capacitance value as well as frequency value. As the capacitance value is fixed, so that's why reactance is changing, because these lines are changing, peak values are changing, starting from 0, then small, then big, then bigger, and the highest. That is only due to the change in frequency.
Yes.
And this block is related to C1, suppose this one, and this
Yes, sir.
block is related to C2.
Okay. Due to
Okay,
different frequency.
due to different frequency.
Yes, sir.
Okay.
So, sir, in that circular sensors, circular sensor means, sir, where the sensor positions are getting circularly rotated. So, sir, there is also changing of the changing of the phase shift, right, sir? So, in that case, how it will perform? So that I
Okay.
want to.
Okay. So you understood the spectroscopy? Then I'm
Yes, sir.
going to the other part. What you are asking? You are asking probably this.
Yes, sir. This one, sir.
Okay. Here we are conducting this experiment at a particular frequency. So
Yes, sir.
please remember that here there is no frequency shift. Means it is not spectroscopy. It is electrical impedance tomography. So
Okay, sir.
this tomography is the concept of changing the electrode position, not the changing of the frequency. Okay. So
Okay, sir.
for getting the image is obtained at a particular frequency. Suppose we are giving the current at 50 kilohertz.
Okay.
We set the current source as 50 kilohertz and we fixed. We didn't change anything. After that, what we will do, we will inject current through two electrodes, measure all the data, changing electrodes either manually or using the multiplexers. After that, we will again change the electrode of current injection from 1 to 2 to 2 to 3. After that, again we will cover all the electrode measurement for voltage measurement. Fine.
Yes, sir.
Like that, we will change the electrode current condition or conduction and voltage measurement.
Okay, sir. So, sir, there is no phase shift or the frequency shift. It's just
Yeah,
for
frequency shift
single.
is not there, but what is there, I am telling you, there is also impedance imaging or tomography, that is EIT techniques, in multi-frequency range. What is done, I am telling you. Suppose we have done 50 kilohertz frequency and we got one image. Then we will change another frequency. We will take 100 kilohertz again. And again we will do the same procedures, and we will take the data, we will solve we will get the or obtain the image, everything is done. So getting the image at different frequency means we have to repeat the entire experimentation at all frequencies. But during a particular imaging experiment, we will not at all change the frequency.
Okay, sir.
Okay,
So
I think,
understood, sir.
yeah.
Sir, another thing is that
Yeah,
Yeah,
please.
Ramesh, it's okay, but give some. It is a very good. You are no, you are keen interest in your research topic and all. Let give the some other people to ask the queries.
Yeah,
okay, sir.
okay, so I will invite you. Let me open my so that I can say learn the name of the participants. May I
Yeah,
know your good name, please?
Tamesh Halder.
Okay. So, Mr. Tamesh or Dr. Tamesh Haldar, please contact me through email. I have my email, okay, at the last slide, or you can collect it from Dr.
No,
Ramesh.
for
Or
the participant, I am sharing the all the resource person detail. If they
okay,
are
okay, okay,
giving
okay.
the
So please,
information.
please
So
communicate.
yes, yeah,
Later on,
serious
also we can
researchers
keep
are there. They
discussing.
can, yeah.
Yeah. So
Thank you,
we are
sir.
we are always there for giving the answer to your query. I will be very happy if
Yeah.
you communicate through email, through phone, or anything else. Okay.
Thank you so much, sir.
Oh, thank you
Ramesh, it
very
is
much.
very nice.
Yeah,
You are asking so many
please, Doctor
question queries
Ramesh.
because yeah, many
Please tell me.
participant they are no lunch break and next session to be start.
Yeah.
We are
So please,
some other is participant. Any queries
yeah,
are there?
please.
We quickly look into some other queries.
Yeah, some Arunesh Dutt Tiwari.
Yes, sir. Good afternoon, sir.
Yeah. Good afternoon. Very good afternoon. Please tell me.
Sir, my question is that you have told the impedance analyzer. Uh,
Mm-hmm.
sir, my question is that the impedance analyzer can detect the any neurological disease?
The impedance analyzer for neurological disease can detect, but as a gold method that is not yet accepted for that. So neurological disorder means if there is any say neurological disorder, you can tell that any epileptic seizure is there, suppose. Okay, so during the epileptic seizure, the entire physiology of the brain changes, and due to the change, definitely there will be some impedance change, but as that change is very minute, so I am not sure how much say accuracy will be there. But definitely that is a very good topic, and that is a good opening. Many people have tried for measuring the brain impedance either in spectroscopy mode or in impedance tomography mode, but
Yes.
generally the tumors are detected. That is the till the success is done. So impedance tomography is useful for detecting the brain tumors. It is possible to be imaged. Okay, so brain
Yes, sir.
tumors can be detected, but other neurological disorders, say you can say that say some Parkinson's disease and all these things, studying those things using EEG, it is more accurate. And for impedance spectroscopy, I'm not sure about that, but that is an open field. We can definitely you can modify our instrument, and nobody can tell that what is going to be there in the next few years. Okay, so
Okay, sir.
possibilities are there, yes, because as the neurological disorder changes its own physiology,
Yes.
definitely there will be some impedance change. One thing I will tell you,
Yes,
there are
sir.
some subdural experimentation.
Mm,
Whenever we will put the electrodes inside the brain,
mm.
that is conducted generally for the animals with the proper protocol. So there, if some brain changes is there, that is always detectable signal is there in case of either EEG or impedance.
Okay, sir. Okay. Thank you, sir.
Okay. Yeah. Thank you very much. Any other question?
Professor Tushar, I have one query, one
Yeah,
question.
please.
Yeah. So normally, we are neuro instrumentation. So it's a combination of MRI, EEG, fMRI, and
Mm-hmm.
this neuroimpedance method, NRF. So many things are there. So when this one, the good aspects of impedance method is low cost and That's what it can be a mass screening gadget we can design in the laboratory. So in that perspective, NIRF and as well as this impedance method, so will give any sufficient result to detect some neurocognition or some other states of the brain.
Yes, that is, the possibilities is there. Impedance is always related with any kind of say changes, either it is anatomical changes or physiological changes. So as I have answered to the question of Mr. Tiwari, so I also tell you that can be related, but how much resolution will come and how much information will be coming in from the scalp, because we are measuring the impedance from the scalp. So definitely